Hello, my name is Brian Ginsburg. I'm a systems manager of the radar team in Texas Instruments, and today I'm here to talk about the fundamentals of modern millimeter wave radars. When I refer to millimeter wave radars, I'm primarily looking at highly integrated radars that are built in silicon technologies. The main application space for these today is in automotive applications, widely used in things like blind spot detection, adaptive cruise control, or regular ADAS features. And these have been in deployment for well more than a decade. In addition, radars are one of the critical sensing technologies that are at the core of highly automated driving or autonomous driving. Outside of the automotive scenario, they are increasingly being used for things that are similar to automotive, like machine vision for robotics, as well as in building and factory automation, primarily to detect the presence and positions of humans, along with more direct human interaction, such as monitoring vital signs remotely or interacting directly with the human machine interface for gesture applications. Let's look at right now the automotive application space. This is an example of a high-end vehicle from circa 2015, where you'd have anywhere between 1 to 6 radars around the vehicle, where the longer range radars would be operating at 77 gigahertz, and the shorter range radars would be operating at 24 gigahertz. As you see, most of these radar functions, adaptive cruise control, blind spot detection, lane change assist, these are primarily focused on highway driving scenarios, which are both very controlled and regular, and everything is moving. And also, each of the radars itself tends to have one particular function. We look at, let's say, a more modern vehicle. A couple things will stand out. First of all, the 24 gigahertz space radars are now completely designed out, and this is due to changes in both regulatory regulations as well as improvements in performance that we'll talk about in the first part of this talk. In addition, the radars themselves now have multiple functions in each location. The forward-looking radar, while still supporting adaptive cruise control for the highway, also has a wider field of view mode for autonomous emergency braking. Likewise, the corner radar, which is used for blind spot detection on the highway, is used for cross-traffic alert in urban scenarios. So by being used at both urban and highway settings, this drives more requirements on the ability of the radar to process slower moving speeds and interact with pedestrians. In addition, there's classes of much shorter range radars inside the passenger compartment and around the vehicle for emerging proximity applications. So today's talk is really going to be broken up into 3 parts. The first section is going to be focusing on the basics of any radar. These are: what can the radar detect, what does it do, what does it measure, and what are its performance limitations. The second section will focus on the frequency modulated continuous wave radar, or FMCW radar. This is the most common radar technology today for millimeter wave applications, including the systems, going to the circuits, and ultimately including the signal processing. Then finally, look at some emerging radar applications that are under active research, including the trend towards getting to imaging radars for much higher angular resolution, different modulation formats beyond FMCW, and then how to extend the radar beyond just circuits on silicon to fully integrating radiators or antennas at the silicon or package level. So let's begin with what is radar. So radar, which stands for radio detection and ranging. The basic principle is you will have the radar or an ego vehicle will emit an electromagnetic wave. This will be emitted into a channel. It'll hit an object, be reflected back, and the radar will measure the round-trip time delay to this object. By measuring the round-trip time delay, you can convert that to the range if you know what the propagation velocity is, which in air, which most radars would be operating at, is the speed of light. The thing that the radar measures, instead of looking at the time delay, if you can look at the frequency shift of the received waveform, you can estimate the relative velocity of the radar to the target. If the target is moving it towards the radar, the reflected signal will come back at a higher frequency. It will be blue shifted in astronomical terms. And if the target is moving away from the radar, the frequency will come back lower frequency, and this will be so-called red shifted. And this is the Doppler effect. And if you can measure this frequency difference is related to the relative velocity through the wavelength. So that means at a basic level, if the radar can measure the time delay and the frequency difference, it can measure both the instantaneous range to the object and the instantaneous radial velocity. The last thing that the radar directly measures is the angle of arrival. And in order to do this, you will need to have some concept of more than one antenna in the system. So shown here is a typical receive array. We'll have multiple receive channels, and this is, you can imagine these are lying in a line. When the reflected signal is coming back towards the receivers, it will be a plane wave, and this plane wave front will hit, in this particular case, since the received signal is coming from the right, it will hit channel 4, slightly before channel 3, before channel 2, and then finally hit channel 1. This small time difference is very small, but this will lead to a phase progression of the received signal across the receivers. And if you can measure this phase progression across the channels, you can then estimate the incident angle. So this we'll talk about how to do this a little bit later, but this relies on the so-called phased array principle. I'm showing it as a receive example. You can actually also do the same thing on the transmitters, where you will actually electronically add in phase delays between transmit elements to project the wavefront in a certain direction. But the angle of arrival does rely on having multiple antennas in either transmitters and or receivers. So I wanted to define a couple more terms related to radars. So a monostatic radar is a radar where the transmit and receive antennas are sharing the same are shared. So you have a single antenna element. This naturally leads to the most compact form factor and allows for precise synchronization of the transmitter and the receiver local oscillators. A bistatic radar has the transmitter and receiver antennas separated, oftentimes widely separated, and it is advantageous in that it can afford very high transmit to receive isolation. A multistatic radar uses multiple transmitters and multiple receivers and measures the delay between all combinations of transmit and receive elements. This offers the greatest flexibility as well as ability to have very widely spaced antenna elements, but leads to challenges in synchronization and complexity and coherence. When we're talking about the millimeter wave radars in this talk, most of them are what I will call pseudo-monostatic. You'll have separate transmit and receive antennas, but these will be very closely co-located, coming from, let's say, the same integrated circuit. In these scenarios, the angle of transmission is equal to the angle of reception, but the separate antennas still provide good transmit to receive isolation, and the close co-location keeps local oscillator routing minimal to allow for precise synchronization. Once we know that what radar can measure, range, velocity, and angle, the key question is how far can it measure? And to derive that, we will go through and derive the radar range equation. Imagine that you have a transmitter outputting power PT into free space through an antenna. This will create a power density at a target object that's proportional to the transmit power and the GT, which is the antenna gain. The antenna gain is higher for antennas that concentrate the power in a smaller field of view. This wavefront will be scattered by the object, and it will create a power density at the receiver. That is the power density here times sigma, the radar cross-section, which we'll talk about in a couple slides. This divided by 4 pi r squared. The power density here will then be captured by a receive antenna and be converted into receive power based off of the antenna aperture. And ultimately, we can see that the overall receive power is just a product of all these terms. As we're looking at this equation, the first thing to notice is that the receive power is related to 1 over width, or in other words, radars have 40 dB per decade path loss. And this is related to the fact that there's isotropic spreading in both the forward direction to the object, and then after scattering by the object, back to the receiver. This means that if you have a similar link budget as in a communication system, which has only 20 dB per decade path loss for a line-of-sight communication system, radar will see comparatively shorter distance. Now that we've captured, we need to say, well, how far can you see? And to do that, we need to determine the minimum signal-to-noise ratio. So we can look at this overall SNR of the receiver as the received power divided by the integrated noise, in this case, KT, F, the noise factor, divided by T measure, which becomes the integrated noise over the measurement interval. And most radars will need to operate with a minimum detection SNR of around 15 to 20 dB to get an acceptable trade-off between the probability of misdetections and the probability of false alarms. And with all of that, you can translate, this is the classical radar range equation, where Rmax is proportional to these terms to the 1/4 power. As we look at this, because it's to the 1/4 power, adjusting any of the terms individually does not significantly help, and you need to make a big difference. 12 dB increase in any one term to double the range. And you also see that, as you would expect, the radar range is increasing with higher output power, higher antenna gain, which means that a narrower field of view, or the energy is more confined in space, as well as a smaller noise figure. The one term in this that still doesn't necessarily make a lot of sense is sigma, the radar. So the radar cross-section is an effective measure of the returned signal power towards the target radar receiver. It actually has the units of square meters as in an area term. It is sensitive to the object size, so it's as you would expect from having it be an area. Generally larger objects have higher RCS, but it is also sensitive to things like the material, the shape, as well as the angle of incidence. And you can see some typical automotive scenes, what the RCS would be, anywhere from 20 dB square meters of a truck down to less than minus 10 dB square meters for a child. In addition, when you're doing actual radar measurements, it is useful to have a couple calibrated objects. Most practical objects do not have closed form solutions of the RCS, but things like spheres and trihedral corner reflectors can be used as well-defined standards with defined radar cross-sections. The other thing to observe, interestingly here, is that, especially for metal objects, the radar cross-section is also a function of frequency for a given physical size. So a metallic object will tend to have a larger RCS at higher frequencies. Shown here is an example of putting this radar range equation to work, comparing a couple different types of radar systems in the millimeter space, a 60 gigahertz indoor radar system and a 77 gigahertz long-range radar system. You can see that there's almost more than a factor of 20 difference in range, which would translate to over 52 dB difference in link budget. And this is accomplished in multiple things. So we have larger antennas and higher antenna gain on the outdoor version, higher output power as well, impinging on the bottom of those antennas. And then, but at the same time, you're also seeing larger objects, typically motorcycles in a highway scenario versus indoors. You're trying to primarily detect humans, which have a much smaller RCS. On the flip side, indoor, because of the fact that indoor scenes move much slower, you can actually have a longer integration time and perhaps much longer to get to improve the SNR through averaging longer. But these are just some illustrative examples, and there's a wide range of parameters to trade off when you're architecting systems to be able to see and examine different scenes. The last thing I want to talk about in the basic section is resolution and accuracy. And so these terms are very critical in understanding how radars operate and what the limitations of radars are. Resolution in the radar context is the ability to separate out two objects. So how closely can those objects be spaced or separated before you can tell them apart? And radar has the ability to resolve objects at any of the dimensions that it can directly detect. So this can be range, velocity, or angle, and it only has to be uniquely separated in one of those dimensions. Accuracy, on the other hand, in the radar context, accuracy is the ability to determine the position of a single object. So accuracy tends to be related to resolution, but in terms of relying on the same underlying parameters, but it is also improves with the signal-to-noise ratio. To see what this looks like, see particularly what resolution looks like, imagine that we have a pulse radar. So in this case, you have a transmitter that's sending out a narrow time domain pulse. This goes out into the channels, reflected off of multiple objects. So when the objects are widely spaced, you'll see the received waveform look like this. You'll get a pulse from the first object, it'll die out, then you'll see the pulse from the second object. These objects are spaced much larger than the resolution limit, and we can clearly identify them as two separate objects. As these objects get closer together, eventually these pulses will overlap. And if you actually look at the envelope of these two combined pulses, you would only see essentially one single peak. It would be a wider peak, but it would be one peak. At this point, you can't identify whether it is two separate objects or one slightly larger object in the midpoint. And then there's sort of a critical distance where you can clearly see a dip between the objects, and this is sort of at the resolution limit. So the looking at this qualitatively, you can say that object reflections in time should be spaced more than a pulse width apart. And that also means that if you have a narrower pulse width, you can have objects that are more closely spaced. It turns out that the fundamental limitation on resolution in distance is not related to the time domain, but rather to the frequency domain, and that narrower pulses, which would correspond to wider bandwidths, have better range resolution. So range resolution is directly related to c, speed of light, over twice the bandwidth. Range accuracy, which is the ability to estimate a single object's position, is also related to inversely proportional to bandwidth, but you see that there's a root SNR factor on the bottom. Because of the minimum detection SNR, you typically will see that the range accuracy is at least, or the accuracy is at least 10 times better than the resolution. Just like we can resolve two objects in range, we can resolve two objects in angle. In this particular case, we are looking at the phase progression across the receivers, and a uniform linear array has the angular resolution, which is delta theta, which is lambda, the wavelength, divided by the total aperture size. And if we have a uniformly spaced linear array, that aperture size is just related to the number of receivers times the antenna, the distance between the antennas. When you have multiple receivers, we're looking at the phase progression. The phase between any two receivers cannot vary by more than plus or minus pi. And this means that there's a maximum unambiguous steering angle that you can steer the beam. If we want to be able to steer the beam over the entire plus minus 90 degrees without any ambiguity, the receivers must be spaced no more than lambda over 2. So this is a Nyquist spaced receive array. And in this case, you can see that the angular resolution for a uniform linear array with a maximum unambiguous steering angle of plus minus 90 degrees is just inversely proportional to the number of receivers. But we can also see here that as we have a higher frequency, you will get a better angular resolution for the same aperture size. So essentially over time, and as we're focused on millimeter wave radars in this talk, radars have moved from lower frequencies of microwave frequencies up into the millimeter wave space. And one of the driving factors, in fact, the largest driving factor for this is at higher frequencies, radars are able to achieve better resolution. So the range resolution, which is inversely proportional to bandwidth, we know that there is typically a wider bandwidth available at millimeter wave frequencies. Similarly, on angular resolution, we just saw that at millimeter wave frequencies, smaller wavelengths, you get better angular resolution for the same aperture, or you can get the same angular resolution for a smaller form factor. And while I don't derive this here, similarly for the velocity resolution is proportional to the wavelength. So at higher frequencies, you will get better velocity resolution for the same observation time. And therefore, we will tend to get better overall resolution, better ability to separate out objects at higher frequencies. So with this, I just want to, at this point, take a look at radar in action before we learn about FMCW radar implementations. So shown in the bottom right is just the camera image of what we're looking at. So this is a simple car driving around in a parking lot. And we'll start with the top right image. So the top right image is just a XY scatter plot of what this radar sees. So as you can see, as the car is moving through, you can see that you can clearly see the shape of the vehicle. You can see the front of it. You can see the trace of the contour along the bumper. And we'll see that the car itself, while a single object, leads to many different detected points. So, in this particular case with a relatively high resolution, 30 to 50 points. If we now look at the bottom left here is an alternative view of range versus velocity, or Doppler. And you can see as the car is moving around, it has a very structured range Doppler plot. You get these straight lines, maybe it'll bend around, but has a fairly well-defined structure. Now, as the car parks and Sandeep comes out and comes back, I want you to keep a look at the bottom left plot. Now, as he's walking towards us, you'll see in the range Doppler plot, it looks very different from the car. And you can see this as he's swinging his arms, now walking away from us. You see, instead of this very strict lines, you see this oscillatory behavior. And this is because while the car is a rigid body, and all portions of the car are roughly moving at the same absolute velocity. When a human is walking, your torso might be moving at a constant linear velocity, but your arms will be swinging back and forth, and that leads to a very different range Doppler plot. And in this particular case, radars rely heavily on the Doppler information to be used in classification algorithms. To summarize this initial section, radars are built around using electromagnetic waves to determine the distance, velocity, and angle to targets. Range is defined by the radar range equation, and that is increasing with higher output power, lower noise figure, longer observation time, and narrower field of view, which corresponds to higher antenna gain. Resolution is, in the radar context, is the ability to separate out two separate detections from two objects, and it can be in any dimension that radar can uniquely measure. Accuracy, on the other hand, is the ability to estimate the position of a single object in the scene, and it's typically much better than the resolution and improves with higher signal-to-noise ratio. And then finally, the motivation to move into millimeter wave radars is primarily due to the fact that resolution in all three dimensions improves as you get to higher frequencies. Next, we will go into a description of the frequency modulated continuous wave radar, which is the main radar system in deployment for most millimeter wave applications. First, though, we're going to take a look a little bit more closely at the pulse radar that I showed earlier when looking at the resolution. In a pulse radar, you'll have a voltage-controlled oscillator generating a continuous wave signal. This goes through a switch, which generates a narrow time-domain pulse that is sent out through the transmitter, emitted into the channel. It'll go out, be reflected across multiple receivers, and then either be down converted by the same carrier or just go through a square law detector, and it will generate a couple of pulses, multiple pulses at the baseband, which can then be detected through correlators. Most long-range radar implementations use some variation of pulse radars, where the transmitter is only on for a limited portion of time. It's also commonly used in the 3 to 10 gigahertz ultra-wideband radar for short-distance applications. But it is not very commonly used in millimeter wave radars. And the primary reason for this is that when looking at the radar range equation, the transmitted power actually refers to the average power emitted into the scene over the processing interval. And in a pulse radar, the average power is limited by the peak power and the duty cycle, and you have a very low duty cycle. Since millimeter wave radars in silicon technologies have limited peak powers, this means that the average power put into the scene will be very low, and you will not be able to see very long distances. So most millimeter radars will cannot use pulse modulation. Well, if we want to get higher average power into the scene, the simplest way is just to send out a constant signal. So just have a constant sine wave that is sent out in the scene. This will go out. So we have an unmodulated sine wave. It'll be reflected by an object. It'll be delayed in time. These two signals can be mixed against each other. And what you will get out at the intermediate frequency is a sine wave whose frequency is related to the Doppler shift. And then there's a phase term. So this will give you the ability to measure moving objects, but it does not give you any ability to measure the absolute distance to an object or to separate out multiple objects that are at the same velocity. This is actually not surprising because the bandwidth of an unmodulated carrier is 0, so there's actually no range resolution. So this is a very simple sensor implementation, and it is useful for measuring moving objects, or the speed of moving objects, for instance, a radar gun, traffic enforcement, but not practically used if you want to be able to separate out multiple objects at different distances. If we want to retain the characteristics of having high average power from a continuous wave radar, but still have range resolution that you would get from a pulse radar, you need to add some type of modulation on top of the carrier. And this is where a frequency modulated continuous wave radar, or FMCW radar, comes about. In an FMCW radar, the carrier of the frequency is ramped linearly over time, as shown here. This ramped waveform is sent out into the channel, reflects off the object, and what comes back is a received waveform that is delayed in time, so it's right shifted due to the round trip time delay, and it's also shifted vertically due to the Doppler effect, or relative radial velocity. In an FMCW receiver, this transmitted waveform is then mixed with the received waveform and generates an intermediate frequency, whose frequency is related to both the distance and the radial velocity. And the actual bandwidth, the maximum intermediate frequency bandwidth ends up being related to the maximum distance times the slope divided by the speed of light. And in practical systems, the intermediate frequency bandwidth is much smaller than the radio frequency bandwidth. And therefore, the received waveform is effectively compressed and has a narrower bandwidth, allows for a lower speed ADC to digitize it. The challenge, the thing that arises, though, from the processing I just showed, is that the intermediate frequency is which is the main thing that we're measuring, is a combination of both the distance and the velocity. And this means you can not actually tell the difference between a static object at one position and a moving object at a different position. And this is a range Doppler ambiguity. All radars actually have range Doppler ambiguity, but it is very easy to see this in the FMCW case, where the range Doppler ambiguity is just a straight line, linear relationship between the range and the Doppler. To resolve this, a traditional or slow FMCW system will instead of transmitting only a single ramp, it'll transmit a second ramp, in this case a down ramp at the opposite slope. And what you will see is that the intermediate frequency here also is the sum of range and velocity terms, but they have different signs. So if you are able to measure both FIF1 and FIF2, you can solve the set of linear equations to determine both the range and the velocity. This works great for a single object, but as you have more than one object in the scene, you will find that this becomes more complex. So with just two targets, what I'm showing on the right is a plot of this range Doppler ambiguity, where you will have, for a single ramp, let's say the up chirp, you'll get one relationship between range and velocity. For a down ramp, you'll get a different relationship, and there's a unique intersection point if you have a single object. With multiple objects, though, with two objects, we find that there are 4 intersection points, 2 which are desired and 2 which would end up being a ghost target. So you are trying to select the real reflections from the ghost reflections, and this becomes increasingly complex. You can decide to solve this by adding more ramps with different unique slopes, but ultimately, for very complex scenes, this is not able to achieve the desired performance. To solve this, modern radars typically will use a fast chirp FMCW system. In this case, instead of transmitting a triangular waveform, they will instead transmit a sawtooth waveform, where you will transmit hundreds of chirps in a sawtooth pattern, each of which is identical. These chirps have a much faster slope, which is called fast chirp, than the traditional triangular wave systems. And then, as we'll go on the next several slides, you're able to estimate the range and the velocity using a two-dimensional FFT within and across chirps. So we'll look at the analysis again. Once again, we're looking at the first chirp here. You have a linear ramp where the transmitted waveform is a linearly increasing frequency. This will then go out, be reflected in the channel, and you will get, the received version will be a delayed version of this transmitted ramp, which is then mixed with the original transmitted ramp. And the intermediate frequency will have a phase term related to the time delay, and then an intermediate frequency term whose frequency is related to both the time delay and the velocity component. So we really haven't solved anything necessarily here. But this is only looking at a single chirp. Now, to be able to estimate both the range and the velocity, let's look at what happens when we're looking at more than one chirp. So how do we handle the Doppler processing? So assume you'll have a sequence of NC chirps, and you have an object that's moving at a constant velocity. The round-trip time delay at the start of each chirp is then linearly incrementing. So from chirp to chirp, we will see an increase in the initial round-trip time delay. So when we put that into the equation, the IF signal of the nth chirp is shown below. And we can, for practical scenarios where, for practical scenes, the drift in the beat frequency can actually be ignored. And what you're left with is you are left with a term where the phase term itself is increasing from chirp to chirp. But the beat frequency term is constant. So this is the same thing shown here. And just to reiterate, across chirps, a single target with a constant velocity has a nearly constant beat frequency and a linearly changing phase. So what do we do with that? First, within a single chirp, you can do an FFT, and that will allow you to estimate the frequency itself, which is related to the range. Then in a given range bin, you can take all of the values of that range bin across chirps, and you can do a second dimensional FFT now in slow time domain, and this will convert the phase progression across chirps into unique Doppler bins. So this is a two-dimensional FFT process, one within a chirp, fast time for range, one across chirp, slow time for Doppler. What is happening in this particular case is that the Doppler FFT, the Doppler processing, is effectively sampling the phase of the carrier with a period of TC, or the chirp time. Since we're only looking at a phase term, we know that the phase will wrap around once it gets past plus or minus pi. So to avoid phase ambiguity in this type of processing, the phase difference must be within plus minus pi between chirps, and that leads to a maximum unambiguous velocity that is inversely proportional to chirp time. So if you want to be able to process higher speeds, you will need to go to shorter and shorter chirps. And this is the continuous evolution of fast chirp FMCW systems. So now, next I want to go into actually some of the implementation details of an FMCW radar. So we'll look at starting at the block diagram. The FMCW radar system, at its heart, there's a local oscillator generation that is creating these sawtooth waveforms. So this is a carrier with a sawtooth frequency over time. It goes through a PA, is sent out through an antenna. On the receiver, it can go through a low noise amplifier, is down converted by the same sawtooth frequency waveform, intermediate frequency analog processing, data converters, and then a DSP. And we'll go through each of these in turn, starting with the unique element of an FMCW radar system, which is generating the frequency modulated carrier. To generate a frequency modulated carrier, you need a frequency tunable element. So we'll start with the basic voltage controlled oscillator. So shown here is a millimeter wave VCO, which is formed out of a cross-coupled NMOS pair and an LC tank. The LC tank has a resonant frequency, but it also has loss, and the cross-coupled NMOS pair in steady state effectively provides a negative GM to compensate for this loss and provide a steady state of oscillation. The actual oscillation frequency of an LC tank is proportional to 1 over root LC, and here the capacitance is the sum of a variable capacitance, or varactor, and some fixed parasitic capacitance coming from things like the inductor and the transistors. In order to modulate this, you can drive the control voltage of the varactor, vary the voltage across the varactor, and therefore tuning the frequency. The first thing that's obvious from this equation is that there is a nonlinear relationship between the voltage and the frequency. This is due to both the square root function as well as the fact that typical varactors have a nonlinear capacitance versus voltage curve. In order to make sure that you're generating a linear ramp, which allows for the signal processing to be clean, you therefore need to do some sort of predistortion where you will generate a nonlinear control voltage waveform to try to generate a linear ramp. So you'll need some sort of loop to estimate the errors and correct for it and calibrate it. This can be done and has historically been done, but it gives you both limited resolution and it is difficult to maintain the absolute frequencies and frequency linearity as things like voltage, process, and temperature are drifting. So instead of relying on an open loop principle, normally when we generate precise clocks, we rely on closed loop principles and feedback. So here you have a phase lock loop, which takes the same VCO, but instead of driving it with an open loop DAC, you embed it in feedback to generate the control voltage to get precise frequencies. And a PLL works by taking the output frequency, dividing it down to a lower frequency, and comparing this frequency to a known reference. This is done with a phase frequency detector, and then that will drive a charge pump and a loop filter, and this will provide closed loop feedback such that the output frequency will end up being precisely n times the input frequency. So now we can generate very precise ramps, or very precise frequencies, but you can't necessarily generate a ramp. If you want to step n, which is the most, one thing that you can control, you'll get large frequency steps, FREF, and FREF tends to be fairly high to be able to have a high reference frequency to suppress phase noise. Alternatively, you can modulate FREF and generate a ramped lower frequency signal. While you've moved which frequency you need to be able to generate the ramp at, you still have to be able to generate a nice ramp signal. So in order to do this, we need to break that trade-off between FREF and the step size to be able to generate fine frequency steps to create a continuous ramp. And this uses, instead of using an integer NPLL, as I showed on the previous slide, you typically would use a fractional NPLL. In a fractional NPLL, instead of having a constant divide value, you will dither between multiple divide values. So shown here are two division values, n and n plus 1. And if you are constantly, let's say, dithering between the two of them, you will, with an average division ratio of n plus alpha, what you will end up having is, on average, the loop will lock such that the output frequency is a non-integer but a rational multiple of the reference frequency. Since you can vary alpha very finely, which is sort of the dithering ratio, what percentage of the time we're at n plus 1 versus n, you are able to get much finer frequency steps and very fine frequency control. The problem inherent in this scheme, though, is that when you're doing this dithering, at any instantaneous time, you are only actually truly dividing by n or n plus 1. So you actually have a large amount of frequency error here at the PFD. And this is the quantization noise. This is essentially quantization noise that is injected into the loop. In order to handle this, fractional NPLLs, you will use a sigma delta modulator to shape the frequency value, division value, such that this quantization noise is primarily located at higher frequencies, and the low-pass loop filter will then filter it out. So now you can have a good phase noise, and you can get very fine frequency steps. There's one more trade-off, however, which is that in order to effectively filter out the quantization noise, you want to have a low loop filter bandwidth. But in order to be able to have a ramp at the output that has a fast ramp rate and have a high-speed ramp signal, you want to actually have a wider loop filter because of the fact that the ramp signal is injected in the feedback path. The ramp waveform itself is also filtered by the loop filter. So you have a fundamental trade-off here between quantization noise coming from the fractional modulator and the ramp rate, and those trade-offs as how you determine the loop filter. There are many techniques to resolve this, including cascaded PLLs, two-point PLLs, and other ways to cancel the quantization noise, which are beyond the scope of the talk, but some of the references at the end will refer to those. And this is an active area of research of how do you generate the fastest and cleanest and low phase noise fractional NPLLs for FMCW generation. Now that we have generated the frequency modulated carrier, a power amplifier is used to take that and produce a meaningful amount of power onto the antenna. Because an FMCW waveform is constant envelope, there's no amplitude modulation, and you can have a fully saturated PA with higher efficiency. In CMOS, these are typically built using multiple cascaded differential common source stages, where the stages, between the stages and at the output, there's transformers that are used for interstage matching networks and final output combining networks. Within the stage itself, the major limitation at millimeter wave frequencies, especially in a common source amplifier, is that there is intrinsic feedback from the output, the drain, back to the gate through the CGD of the device. This can lead to instability and ultimately is a source of negative feedback that reduces the gain of the system. So to stabilize the amplifier, a commonly used technique is to use a second capacitor driven with an opposite signal that cancels the charge from the drain back to the gate. So if CN and CGD are about the same size, but they have opposite signs, the sum of I1 and I2 is 0, and there is no feedback. So this will break the feedback from the drain to the gate, stabilizing the amplifier. It's actually also a form of positive feedback overall and can actually boost gain. So there's a common technique a widely deployed technique throughout millimeter wave radar deployments. Finally, the maximum power that can be delivered to the antenna is limited by the voltage, which cannot be very high in advanced technologies, as well as the device width, which cannot be too large. Otherwise, the parasitic capacitance makes the impedance transformation ratio between the power amplifier output and the antenna to be too large. To overcome this, typically higher output power is developed through power combining. So shown here is a parallel power combining network where you'd have multiple identical paths combined through a transformer with the currents summed at the output. Now let's move on to the receiver. The receiver is actually much more challenging in an FMCW system than the transmitter, and this is primarily because of the very high dynamic range that must be handled. So there are three main things that are driving the large range in signal levels at the receiver input. The first, as we saw in the radar range equation, is the fact that the received signal power is dropping by 40 dB per decade, and you must be able to simultaneously handle near objects and far objects. The second one is that there is within a single range bin, there can also be a very large RCS variation between the largest objects like a truck and the smallest objects like a child. And then finally, in a continuous wave radar system, the transmitter and the receiver are on simultaneously. And no matter how much isolation you try to provide, there will always be some coupling paths from the transmitter to the receiver, which will establish a leakage at a very close range. And even if you maintain separate antennas in practical deployments, things like reflections from the environment can lead to this coupling level. I did not know this before I got into radar systems, but apparently paint colors are derived by embedding small particles inside a dielectric. And for certain paint colors, like bright silver, those particles are metallic. So if you actually look at a bumper, which is typically placed in front of a medium and short range automotive radar, a bumper is a low loss, relatively transparent plastic with a thin layer of paint, which can be of very high permittivity on the outside. And this will lead to a large impedance contrast and leads to large reflections that will both attenuate the signal going through and can lead to jamming of the receiver. And so you can get, even if you have separate antennas, you can still get fairly low isolation levels between the transmitter and the receiver, or poor isolation levels of only 20 dB. And so the receiver must be able to handle all of these terms simultaneously. When we talk about very long-range radar systems, non-millimeter wave, or let's say for planes, this is why they always use pulse radar configurations where the transmitter and the receiver are not on simultaneously, and this leakage term is not relevant. So how do we handle this entire dynamic range? Because it can be well more than 120 dB. So to start with, in the world of pulse radars, there's the concept of a space-time filter. So when you have a pulse sent out, the reflections that are coming at closer time are coming from closer objects, and they will therefore be larger. And the reflections that are coming at longer time will be smaller. So a space-time filter increases the gain of the receiver as time increases. In an FMCW radar, you can get the exact same functionality by simply using a high-pass filter, where the high-pass filter will suppress the close-in waveforms, like the bumper reflection and near-in objects, but not suppress the far-out objects. The RCS variation within a single range bin must still be handled by the instantaneous dynamic range of the entire system, including the receivers and the ADCs. So typical modern FMCW radars for millimeter wave applications might use a second-order HPF to suppress the bumper reflection by up to 40 dB, and then use ADCs that have, let's say, 10 to 40 megasamples per second with reasonable effective number of bits, but very high spurious-free dynamic ranges, so that large objects will not generate another tone that is a ghost object at a nearby range bin. Looking more closely at the RF stages have to handle the full dynamic range because the channel compensation is done at the baseband. So therefore, these tend to have very high input compression points and a very low gain. In a CICC implementation, you will typically have an active mixer directly loading the antenna. In a CMOS receiver, they will typically use a passive mixer to minimize flicker noise and then insert a low gain, low noise amplifier before the mixer. And in this case, the LNA uses basically the same topology of transformer coupled common source stages like in the PA, but optimized for low noise as opposed to high output power. The last thing to discuss when just talking about dynamic range is the impact of phase noise. So let's expand our local oscillator to include both the frequency modulation, potentially phase modulation, as well as the phase noise term phi n of t. In the down conversion mixer, the phase terms are subtracted from the transmit and the receive waveforms. And what you will get back after doing some trigonometric identities is the intermediate frequency, or the output of the mixer, is the desired term plus a residual term, xpn of t, which is this term over here. So AIF sine phi IF t times the sign of the differences in the phase noise of the transmitted waveform and the received wave. So as the phase noise term was the product of the signal-related component and the residual phase noise component in frequency domain, this is the convolution of the signal component, so a reflected object's signal, and this residual phase noise term, where the residual phase noise term in time domain is the difference between the same noise term but delayed. As you can imagine, with a very small time delay, or for very low offset frequencies where the phase noise is not very much, these are highly correlated and you'll get a large suppression. But at larger time delays, you'll get, or wider offset frequencies, you will get less suppression. And this leads to a correlation factor shown here, where you can get a very large suppression of close-in for closely separated objects or close objects, but far less suppression for far objects. This residual phase noise term is then convolved with the signal, with each target's reflection, and leads to a phase noise skirt around that object. Critically, this means that if there's only a single object in the scene, the phase noise does not impact the sensitivity to be able to detect that object. But if you have multiple objects, or including perhaps the leakage from the transmitter to the receiver via the bumper reflection, the phase noise then will ultimately limit the ability to detect both objects at the same time. So the overall dynamic range of objects in the scene is limited. Finally, just at the architectural level, how do we estimate angle? As we discussed earlier, angle is estimated via the phase progression across multiple receivers. And the way that this is practically done is using some type of beamforming shown here, which is the most common implementation in automotive scenarios, is to use digital beamforming, where all of the receivers are processed independently using a shared local oscillator, but have separate down conversion mixers, basebands, and data converters. And then the DSP will do all the computation and beamforming. This has the highest hardware complexity because you have to have all receive chain elements are duplicated for all the channels, but it allows all the receiver streams to be processed in parallel and ultimately can support the highest speed scenes without any velocity or motion artifacts. You can also adopt approaches that are used in 5G systems using radio, RF, LO, or baseband beamforming or hybrid architectures. And these are also deployed in emerging area research at some trade-offs of complexity and velocity performance. The way that the digital beamforming works is that we're digitizing each of the received samples, and for a single object, you will see that there's a linear phase progression across those antennas. And by simply taking an f of t across the antennas, you're able to estimate the angle of arrival. Given the fact that, with very few antennas, f of t's of likely length 4 can just be implemented as different types of matrix multiplication more efficiently. However, radar, while it does very well in terms of resolution for both distance and velocity, the angular resolution is actually quite limited. So there's a lot of research on how to improve that angular resolution. I'll talk about imaging arrays in the last part of the talk. But there's a number of super resolution techniques that people have looked at, things like music and esprit, which are intended to improve the angular resolution, but have some limitations either in terms of stability or usability or applicability under low SNR conditions. In order to improve the angular resolution, though widely used in conventional automotive radars, is the concept of MIMO beamforming, or multiple input, multiple output system, where you are using multiple transmitters and multiple receivers simultaneously. And to see how this works, I'm just going to start with an example of 2 transmitters and 3 receivers. Imagine that you are first transmit with transmit antenna 1, and you will receive the waveform. You will get a phase progression across the receivers, 1 e to the j phi, e to the 2 j phi. Next, we will turn on transmit 2, turn off transmit 1. Since transmit 2 is spaced 3 lambda over 2 from transmit 1, it will have a overall bias of e to the 3j phi, but the phase relationship between each of the receivers will still be the same e to the j phi between each neighboring receiver. If we were to take these 2 arrays, or 2 vectors, and we were to stack them next to each other, you will get a phase progression from 1 all the way to e to the 5j phi. And this is equivalent, it's exactly what you would have had if you had one transmit antenna and 6 receive antennas like this. So a MIMO radar, we call this the virtual array. In a MIMO radar, this is the virtual receive array. And the positions of the virtual receive array are at the convolution of the transmit and the receive antennas. And if the number of elements in the virtual array is the product of the number of transmit and receive antenna elements. In this example, where there's only 2 transmitters and 3 receivers, we took 5 physical elements and generated 6 virtual elements. It's not a huge complexity savings. But you can imagine, let's say you have 5 transmitters and 10 receivers. Now you have 15 physical elements, but you're generating 50 virtual elements. And so this leads you to get a large increase in the number of virtual elements for a given amount of physical complexity and is widely deployed. Finally, just look at the overall signal processing steps. We've talked about how in FMCW radars, we'll use FFTs in fast chirp, fast time for range processing, FFTs in slow time for Doppler processing, FFTs across antennas for angle processing. After this is done, you will get a data cube that has axes of range, velocity, and angle, and it'll be a matrix, and each element will be the receive signal level in those range, velocity, angle location. The next step is to process that and make sense of it. So radar signals are typically very sparse. Most of the bins inside the data cube are error, and there's minimal reflections. So the detection is the going from a data cube and identifying points where there are potential targets. After a detection, these points are localized, going through clustering, tracking, and occupancy grid, and ultimately classified, and decisions are made. The key element here, the first thing to look at is this transition between a complete data cube, a continuous data cube, and discrete set of points. So detection is the process of separating out candidate targets from noise, clutter, and interference. And in this particular case, clutter in the radar context is anything that is undesired. And clutter really depends upon your perspective. So as an example, many of you are familiar with a Doppler weather radar, where those scans on a screen where you see a circular scan going around, and you'll see bright colors wherever rain droplets are. There, a Doppler weather radar relies on backscattered signals from rain droplets. So rain is the signal of interest. In automotive radar, rain is a backscatter from rain droplets is primarily considered clutter and is uninteresting. Clutter can also be from things like ground reflections or anything else that is not of interest. Noise is self-explanatory, is primarily coming from electronic sources, additive white Gaussian noise. Noise itself, just like in communication systems, tends to be fairly stationary, so constant over time and distance. Clutter, however, is not. So the reflections from the ground vary over distance, and reflections from rain definitely vary over time. So clutter has both spatial and temporal variation. To account for this, radars will use various ways to estimate what the local level of clutter and noise is. And one way of doing this is using something called a constant false alarm rate, or CFAR detector. So CFAR generates a local estimate of what the noise and clutter level is. It does that by, let's say we're trying to determine if cell Y in the middle here is a reflected point. The CFAR detector will skip a couple neighboring cells around it and then look at the M window cells on both sides and do some sort of processing to estimate what the clutter level is. Then based off of what the clutter noise level is, it will give a scale factor, says how much above that do I need to be, let's say 10 dB, then ultimately compare this point to the scaled version of the clutter level. And to estimate the clutter, you can use very simple schemes like averaging, CFAR-CA, or more complex schemes like ordered statistics that looks for the kth largest sample. Which particular CFAR scheme you want to use is it depends on the type of scene you're looking at. It's part of radar design and research of designing optimum detection algorithms for particular radar scenes. After detection, there's a number of higher level algorithms that are used. As we saw in the video earlier, a single object like a car can have many point reflections. So clustering is combining multiple of those points into an actual object. Tracking is taking the recorded data from one frame and associating that with recorded data from previous frames, knowing that objects have a finite motion models. So as the car is moving, it can't instantaneously jump from one place to another place, but it will be moving at a constant, at a reasonably constant velocity with maybe some acceleration terms. And so tracking will associate the predicted state of an object from its historic track with the current points in the scene. This can be done using, for example, Kalman filtering. Occupancy grids are another higher level algorithms that are primarily looking at static scenes and will associate where there is a static object as the ego vehicle moves through a scene. And then finally, classification is identifying what an object is. And as we saw, classification oftentimes relies on things that are not strictly range and angle, but oftentimes heavily uses the velocity component to classify and determine information. To show what this looks like, this is an example of FMCW radar signal processing. So after the second dimensional FFT, you will generate a Doppler range heat map. So in this scene, you'll see that there's a lot of reflections at the 0 Doppler bin. So this is all the reflections from the static environment, from the ground, from the trees, and the car, which is moving at a constant velocity away from the radar, will have be a point reflector here with a non-zero velocity. After we do detection and angle estimation, we can plot this into an XY plot. This is a top-down view, and the color here is the Doppler. And you can see that you get a number of points that are in the static detection from the 0 Doppler bin, but then the car is clearly showing up here with a non-zero velocity. To summarize, modern FMCW radars generate a linear frequency sweep using a fractional NPLL that is then transmitted through a saturated PA. The receivers need to handle a very large dynamic range due to the large transmit-to-receive leakage, as well as the near-far problem due to the decreased reflective power from distant objects. In the signal processing, range is proportional to the intermediate frequency after down conversion. The Doppler is related to the phase progression across multiple chirps in the sawtooth pattern. And then finally, the angle is determined using digital beamforming and MIMO techniques, where the phases between multiple transmitters and receivers is captured. In the last section, I'd like to talk about some new topics that are emerging in radar research, including imaging radars to achieve higher angular resolution, looking at other modulation schemes, and then finally touching on. So, modern radars that are typically used in, let's say, a corner radar scenario in a vehicle might have between 2 to 3 transmitters and 3 to 6 receivers, giving you at most 18 virtual antennas and roughly 5 to 6 degrees of angular resolution. However, and this is sufficient if you are primarily looking at moving objects that are widely separated out due to their sparse Doppler signatures, but are not suitable for imaging the static environment. And just to look at a couple of very challenging use cases, imagine you are driving on a highway in the rain. As you know, as you probably have seen, if a motorcyclist is driving in the rain and it's heavy rain, they will typically go under an underpass and park themselves to protect themselves from the rain. And in this case, the radar must be able to successfully detect and separate out the motorcycle from the overpass above them. In another even more challenging scenario is where there is a unsafe object on the roadbed, for instance, a blown out truck tire that you have to decide whether you can drive over it safely. And this is sitting on top of the road and has only a very small height that you must be able to detect. These are leading to angular resolutions that are less than 1 degree, sometimes much less than 1 degree, approaching LiDAR-like requirements. To see how we fulfill those requirements, we will start with the fact that the angular resolution is inversely proportional to the aperture size. So if you wanted to get to 0.3 degrees of resolution, you would need a 70 centimeter aperture. And at dense array of 70 by 70 centimeters spaced at lambda over 2 will lead to over 120,000 virtual antenna elements. This would be great if we could sell thousands of channels per car. Semiconductor manufacturers, we would love that. But it leads to impractically large form factors as well as incredible complexity. Even if you wanted to, let's say, only achieve 1 degree angular resolution, both azimuth and elevation, you're still talking about more than 10,000 virtual antennas. It is clear that you're not going to be able to get 100 physical channels on a single chip. In practice, the number of transmit and receive channels you can fit into a single chip is limited by, among other things, the heat and the fan-out. So it becomes essential for how to build up a coherent imaging radar using multiple chips. And for that to happen, you must share two things. They have to have a common local oscillator frequency and local oscillator timing and phase. And they also must have a common ADC timing. The requirement on the time alignment is actually much stronger at RF. This has to be at the 5th level, but still, even at IF, when we're sampling the IF waveforms, errors on the ADC sampling instance at the hundreds of picoseconds level can also lead to an appreciable angle mismatch between antennas. So how do you actually practically implement this? So this is an example from a 77 gigahertz chipset presented a couple of years ago. This is the actual clock system showing the single chip configuration. You have a high frequency PLL that's both generating the clock, ultimately the clock to the data converter, as well as a high frequency reference to be able to improve the phase noise of the synthesizer and suppress the fractional and quantization noise while still maintaining fast ramps. Here, the ramps are actually operating at 20 gigahertz or 1/4 of the carrier frequency. So when we look at multiple chips, we need to be able to synchronize. So the 20 gigahertz carrier from the master device is actually sent out onto the board. It's sent out to the slaves. On the slave devices, they would take the 20 gigahertz signal as an input and directly drive its upconversion of the multipliers for its internal LOs. In addition, the ADC clock is released synchronously on all the devices, where there's a frame sync that starts the ADCs, the data converter clocks for all the chips. This is also routed out onto the board. And further, in order to have the master device where you have multiple of these devices, where there's one master and multiple slaves, and for them to have the same sampling instance, both the frame sync and the 20 gigahertz signal are routed out onto the board and then looped back on the board to the master device. And this means that if you have length match routing between the master and all the slaves, there is no systematic time error at either the local oscillator or the ADC sampling instance. What this looks like in practice is an example where there's 4 of these chips that are cascaded on an evaluation board. There are 16 receive antennas at the top, and 12 transmit antennas on the bottom. 9 of these transmit antennas are uniformly spaced in elevation, and then there are 3 that are offset in azimuth. This ends up having theoretically up to 192 virtual channels, although there is some of them are overlapping with each other. And so ultimately this is able to simultaneously achieve around 1.5 degrees of azimuth resolution and around 10 degrees of elevation resolution. This is an example of what that imaging radar is able to observe in a practical parking lot scenario. On the left, you can see 2 cars that are barely visible in the image, but are cleanly separated by 1.7 degrees in the radar image. You're also able to see a small person separated from 2 vehicles, as well as things like the curb, grass, and trees simultaneously when just looking at the static environment. This can get much better performance results than you would get from a typical small channel count 4x3 radar system, but it's still quite far away from what is required to get to the ultimate 0.3 degrees of angular resolution that is targeted for a full level 4 autonomous vehicle. Is the need to generate much larger numbers of channels. The other practical problem is that 70 centimeter box becomes impractical to include in the front of a vehicle. And so one approach and continuing area of research is to push the frequency higher. Shown on the left are the atmospheric attenuation or atmospheric absorption. You can see that there's a low atmospheric absorption at the 77 gigahertz band. There's also windows available at 140 and 240 gigahertz. And these would lead to roughly a 3x reduction in the outer dimension of such a radar system. in order to achieve a 140 gigahertz radar, there are some key considerations, including the complexity of integration, how you are able to increase the number of channels, as well as integrate both the circuits and the radiating elements. In addition, you have to be careful of how you are able to process the overall scene dynamic range. When we look at the overall SNR, as we go to higher frequencies, the lambda term is decreasing, the output power is decreasing, and the noise factor is increasing. Simultaneously, phase noise is increasing proportional to frequency squared. And what really we need to have is we want to have constant SNR at the same range, and you want to have the constant phase noise. In the next section, I want to talk about some other modulation formats. We've been heavily focused on FMCW after a brief foray into pulsed and CW radars. Those are not the only modulation formats that are used. One example here is a step frequency continuous wave system. Here, instead of generating a continuous linear ramp in frequency, this is a discrete ramp with multiple steps. And then for each step, the received waveform is processed and digitized. You can go through the math here, but essentially what this shows is that in an FMCW waveform, if the bandwidth, ADC samples, and the step height is properly determined, this ends up being just the discrete approximation of an FMCW ramp, and you can get equivalent baseband waveforms. So much of what we learned about the FMCW processing would apply here. Another waveform that is getting increasing prominence is orthogonal frequency division multiplexing, or OFDM. This is widely deployed in communication systems, Wi-Fi, 4G, 5G, and therefore this is highly attractive for systems that are wanting to leverage the communication infrastructure or to have a single system that does both communication and radar. It transmits multiple carriers at the same time within one symbol, and therefore the receiver must process the full IF bandwidth. The IF bandwidth and the RF bandwidth are the same. There's some techniques to try to break this trade-off as well. But most challenging in this scenario is that an OFDM radar would be very similar to a full duplex communication, where your transmitter and your receiver are on simultaneously at the same frequency. And unlike in a pulse radar with a space-time filter or FMCW with the equivalent high-pass filters, there's no elegant analog way to suppress the close-in reflections. Instead, most of these systems are developing research techniques to cancel out the transmit-to-receive leakage, and how to do that robustly without deteriorating the received dynamic range is a continued area of active research. The last modulation format I'll talk about, which is gaining increasing prominence, is a phase-modulated continuous wave radar. This was after a significant research at IMEC. This has now transitioned into commercialization, and it was proposed due to its simplicity of implementation in advanced CMOS technologies. And we'll just walk through it. We're an PMCW radar. You'll have a continuous wave carrier here. This will be phase modulated, oftentimes with just a simple BPSK code. That'll be transmitted out, received down, mixed to the same carrier, and then the received waveform is correlated to this code, and ultimately this is processed to determine the same things of range, Doppler, and angle. In this particular case, the RF hardware is very simple. You have an unmodulated carrier versus a ramped FMCW generator, and the vector modulator here for this can also be very simple, especially if it is simply a BPSK or two-phase, binary phase modulation. The way that the processing is done is that the received waveform itself is digitized, and then ultimately in the DSP, the received waveform is correlated to shifts of the code template. And you will do this for all possible shifts of the code template from 0 to the maximum unambiguous range or the maximum desired range. And this effectively calculates the autocorrelation of the code sequence across the range dimension. So one thing that's obvious is that the code itself, the code length and time must be longer than the maximum round trip time. And as we'll go through a little bit later on, there's some particular properties in the autocorrelation of this in order to have good dynamic range performance. The way that these codes are structured overall to generate the full PMCW is that you will have an inner code of number of chips LC. This will have a total length LCDC. This has to be longer than your maximum round trip time. This is repeated to M times. And then you can also have an outer code that's applied to this, where this outer code can have the outer code is multiplied times this inner code, and this can be used to, for example, encode multiple transmitters so that they can be simultaneously transmitting for a MIMO operation. The inner PMCW code is the major limiter of performance in the range dimension. Since the receiver basically calculates the autocorrelation, you would like the code to have a very favorable autocorrelation property, so a very high peak to side lobe ratio. Similarly, in order to handle multiple radars in the scene, you would want a code that has good cross-correlation to other codes in the same code book. Just as some simple examples, let's say you're using a pseudo-random number code. These pseudo-random number sequences are widely deployed CDMA systems, but the autocorrelation dynamic range is limited to 20 log to the number of symbols inside the code. So if you have like a length 1023 length code, you only have about 60 dB of peak to side lobe ratio. And this is much lower than peak to side lobe ratio, and this is much lower than you would have from the range of reflective power from a near to a far distance object in a long range radar. There are other code sequences like an almost perfect autocorrelation sequence as shown on the right. Here, the side lobe is identically 0, except at one particular location at half the distance, where you have a large negative peak. And therefore, this works very well with a code length that is twice your maximum desired range. Although the autocorrelation does tend to degrade with the Doppler shift. There's multiple other codes, and this is refer to some of the references at the end for. The block diagram is very simple, where you have a CW on the transmitter, a simple vector modulator or binary phase modulator, and then ultimately most of the processing is done in the DSP where the complexity is. The way that this DSP processing is that initially you will correlate to all the offsets of this sequence on the inner code, and here typically these will be a bank of parallel correlators, so you can process all the code shifts in parallel. These codes are then accumulated multiple times with the repetitions of the inner code to improve the SNR. Ultimately, you will have a discrete Fourier transform across slow time domain. This ends up to estimate the Doppler component. It turns out that everything after this accumulation is basically the same as FMCW signal processing. So the velocity estimation and the angle estimation are the same, but the fast time domain FFTs are replaced by correlators and accumulators. One thing to note here is that the correlator complexity itself ends up being proportional to LC. So in order to have low complexity signal processing, you want to have short codes. At the same time, you want codes that give you good auto and cross correlation sequences, and that is one of the fundamental challenges of a PMCW system. This is an example of a modern PMCW system using a GMSK code domain MIMO radar that was introduced last year at ICCC. While the block diagram looks much more complex, it actually is quite similar to what we showed earlier. So on the transmitter, there's an unmodulated carrier. This is then going through the vector modulators where the code is applied. Here, the code is actually coming from high-speed DACs. So you can have more complex codes that provide more flexibility as well as waveform shaping to meet the spectral emission requirements. On the receiver, the LNA signals are just going in and down converted and processed through high-speed, low-resolution ADCs. One of the challenges in PMCW, similar to OFDM, is that the transmit to receive leakage cannot be canceled by simple filtering. So instead, they have developed an active cancellation loop where a replica of the transmit signal is generated through a DAC and fed into the RF domain and canceled at the mixer input. For more details, you can refer to this publication, but this is an area where it is intended to be used for highly digital systems and for compatibility with more advanced. The last area that I'll briefly touch on is where the integrated circuit ends. For long-range radars, they typically have high-gain antennas, 10 to 20 dBi. These can be very long antennas, physically large, and at 77 gigahertz, don't practically fit on a circuit or on silicon or package. and are implemented either at the PCB level or at a 3D housing level using waveguides. But for shorter range systems, the antenna size now has actually become smaller than integrated circuit dimensions. And so these can be directly integrated on the package. I show two examples here, a 60 gigahertz radar that was intended to be used for short distance human-machine interface applications, where this uses an EWLB or fan-out wafer level package, where the chip is embedded inside a larger mold area, and the antennas are just implemented as patch antennas or dipoles on the mold. Alternatively, another implementation of package-based antennas would be this undermount BGA. Here, the silicon is on the bottom side of using a conventional BGA substrate. The antennas are on the top side, and with patch configuration. It's difficult to see on this view at the right, but I'll just highlight where the antenna positions are. It says 4 receivers in a 2x2 grid, and then 3 transmitters in an L shape. This will give you a larger L-shaped MIMO array configuration. Above 100 gigahertz, there's a lot of research that's showing that the antennas themselves can actually be implemented on the silicon. Applications for these include human-machine interfaces, parking, in-cabin applications in automotive. So in summary, millimeter wave radars have established market dominance in automotive for ADAS and highly automated driving scenarios, and they're emerging into industrial and in-home applications. Radars have moved into the millimeter wave space primarily to get better distance, velocity, and angular resolution at a given form factor. Frequency modulated continuous waveforms are the dominant format for automotive applications due to the simplicity of implementation, as well as the simplicity and elegance in handling the near-far problem, and achieve very high signal-to-noise ratio. As we look forward, one of the major challenges is how to address static scene processing, where you need to move to an imaging class of radars with much higher numbers of channels, and how to do that in a cost-effective way, and to achieve the desired performance, you must achieve very high levels of coherence and synchronization across the array. New modulation formats are being adapted and considered to get additional flexibility, better interference processing, better velocity processing, amenability to communication systems, as well as amenability to implementation in newer process technologies. And then finally, the area of radar research does not end simply at the transmit and receive outputs electrically, but also includes integrated antennas at either the package or the silicon level, primarily as we go to higher frequencies or to go to shorter range applications. With that, thank you for your attention, and open this up for questions. Thank you very much.
Okay, thank you very much, Brian, for that wonderful talk. That was an excellent presentation. I'd like to remind the audience that you can submit questions online. Please do so. Right now, we actually don't have any questions from the audience, so I would really encourage you to submit some. This is your one chance to ask the author directly about any of the topics that were given in this presentation. I guess I'll start off by asking my own question. First, Brian, are you on the line now still?
Yes, I am.
Okay. It's very interesting, the different modulation methods that people are looking at, FMCW, PMCW, OFDM. What do you see in the future, actually? Do you see one dominating over the other, or is it really going to be, different modulations are going to be used for different applications, more appropriate for some applications or work better for some applications versus others? And then, they all have their shortcomings. So what I also wonder, has anybody ever talked about, or could you envision like multiple modes, right? Where, maybe you time multiplex somehow between these different forms of modulation. And has that ever been considered? And is there any merit to something like that?
That's a great question. So I think that at least in automotive, at least for the next foreseeable future at 77 gigahertz, variants of FMCW will continue to be the dominant modulation format. And I think eventually I expect that this will ideally turn into some sort of a standardized scheme in order to be able to share the spectrum. And this is based off of both the large installed base and the just the advantages in the, to handle the near far problem effectively. In other frequency bands and for other application spaces, that definitely won't be the case. For instance, there's a working group in Wi-Fi Alliance right now that's looking at trying to blend in sensing and radar into Wi-Fi based signaling, and there, it's very hard, it's straightforward to see that would most likely be some sort of OFDM based signal. And then at higher frequencies, as things are moving beyond, into higher frequencies as spectrum opens up, I think we'll be looking at, entirely new modulations where you can start fresh that probably have better characteristics in terms of handling larger numbers of total users simultaneously. That being said, I think what you will see, rather than being able to switch between one modulation format and the other, is that you will see, I describe these as sort of independent modulations, but these can be combined. For instance, you can already, most FMCW radars would already include some sort of phase modulation, slow time domain phase modulation, that's being used to encode the multiple transmitters for MIMO operation. And you can also increase the, you combine them at a higher rate where you will actually have a phase modulated and a frequency modulated signal simultaneously, once again, either for better handling of multiple transmit antennas for MIMO, or to be able to better handle interference when you have multiple radars operating in the same space. So I think that you will see blends of these, but for the most part, at least in 77 gigahertz, FMCW will be the dominant underlying technology, and other frequency bands, I think you'll see different dominant waveforms.
Okay, great. All right, now we have some questions that have been submitted. Again, to the audience, I encourage you to submit questions, please, using your Q&A form. We have a question from Ru Ma, MERL, and his question is PMCW radar better immune to radar interference compared with FMCW radars? If so, why?
So that is an interesting question. So I think in general, PMCW and FMCW radars behave very differently to interference. In a PMCW radar system, the interference, since the PMCW has a wide instantaneous frequency bandwidth, any interference essentially any interference in the scene will always impact the PMCW system, but it will always be spread by the coding gain that you get. So you get when you have interference present, you get a uniform increase in the noise floor, but it's fairly well behaved. In an FMCW system, the interference for the most of the time, and if you have a narrow band, like let's say another FMCW system, an FMCW transmitter, and you have a victim FMCW receiver, you only are impacted, your received signal is only impaired if the transmit waveform, the aggressor, is within the intermediate frequency bandwidth of the receiver. And this means that most of the time you have zero interference, and then occasionally you'll have a very high level of interference. So the interference characteristics are very different. When we've been doing a lot of, we spend a lot of time looking at this because this is a really significant growing problem in the industry. And our analysis is that with the sort of state-of-the-art mitigation techniques, FMCW tends to outperform, or is at least as good as PMCW systems in terms of the final probability of detection and probability of false alarm in the presence of interference. But in order for that to happen, there needs to be some type of handling of some type of additional waveform control that I didn't cover in this talk, but that certainly that there are definitely references that have come out in the last couple of years and are still coming out on how to both avoid interference and how to handle it when it comes. So yeah, there is no clear answer that one modulation format is uniformly superior, but at least our analysis is that FMCW is at least as good as PMCW, but they're fairly similar.
Okay, great. Again, to the audience, please submit any questions that you have online using your Q&A form. Our next question, it's actually two, but I'll take them one at a time. Professor Kenneth O. of University of Texas at Dallas. He says, great talk. What is the equivalent data rate needed for PMCW radar?
So for PMCW radar, the data rate is related to the instantaneous RF bandwidth, which is related to the range resolution that you want to achieve. So for instance, if you, like a state-of-the-art short-range radar system would typically have around 800, 900 megahertz of RF bandwidth, in which case the IF bandwidth would be half of that. You'd have an IQ receiver with half the bandwidth. So you're talking between 400 and 450 megahertz of IF bandwidth, and then 1 to 2 gigasample per second ADCs to digitize it.
Okay, great. And I'm curious, could you actually discuss the bandwidth in context of the length of the code? That's actually a question from me. What's sort of the trade-offs there and the length of the code and the bandwidth?
So the length of the code is going to be related to the, at the minimum, it's going to be related to the maximum range that you want. And the bandwidth ends up being related to the range resolution. So the total time length of the code is related to the range, maximum range, and the total bandwidth is related to the range resolution. When that works out, that means that the number of the code length in just samples as opposed to time is some factor, either 1 or 2 times the maximum range divided by your range resolution. So in this case, as I was going back to that example before, where you have a short-range radar operating at close to a gigahertz bandwidth, which would be around 15 centimeters of range resolution, and you want to see, let's say, 60 meters, that means you would want to have, between around, the total code length would have to be around 800 chips if you using something like the 8-pass sequences that I was showing, where you need where there's an ambiguity to half the code length. So but the number of the number of codes in your code book, the number of codes in sequence has to be related to the maximum range divided by the range resolution.
But if I'm sorry to follow up, but if I have a given resolution, so that translates from what you're saying to a given bandwidth of the radar, but now I want to progressively increase the distance, the range. Wouldn't at some point you need more bandwidth in the transmit and receive paths to accommodate a longer and longer code for a given resolution?
No, so you don't. In this case, in a PMCW system, you do not need to increase the bandwidth to get longer range. You just need to increase the total code length. So the bandwidth is going to be related to the chip rate, so how quickly you're moving through the codes. But the total time that the total, but it's not related to the total length of the code.
Okay, good. All right. So another question from Professor Ken O at UT Dallas. Could you talk about the back-off requirements for OFDM radar?
That is a good question, and one that I don't think there's a lot of study at this point on, because of the fact that you're not actually trying to communicate, and you have complete control over the symbols that you're putting out. You can do pretty sophisticated, like some of the peak to average power ratio reduction techniques. Some pretty advanced ones in terms of what codes, what are the symbols that you would put, or what are the symbols that you would be using in your OFDM symbol. to reduce the peak to average power ratio. So I don't actually know what, I don't have a good answer for what would be needed backoffs, but the linearity required in a radar system would be less than the linearity that you would typically require inside a communication system. And therefore, I would expect that the backoff on the PA would also be less. But I don't have any absolute numbers to share.
Yeah, makes sense. Makes a lot of sense. Okay, again, one more reminder to the audience. This probably is going to be your last window here to submit questions, so please do so if you have any remaining questions. And there's actually one question left on the Q&A. Hopefully we'll get some more. It comes from your company, Brian, from Texas Instruments. Swaminathan, I'm not sure I pronounced that correctly, and your last name was chopped, so and I probably butchered anyway, so it's probably better that I just stick with that. He says, excellent talk. What are the benefits of integrated radars aside from cost? So I guess it's a performance question. Is there a benefit, I guess, from a performance perspective to, in the domain of integrating the radio?
So one of the biggest advantages that you get from integrating the radio is, obviously there is a cost to the form factor, but compared to discrete implementations, it's a lot easier to maintain channel matching. And that is really critical to get good angular resolution. So intrinsically, we're able to get much better matching if you have multiple parallel channels on a single die. And this means that your angular resolution, your angular side lobes, all of your angular performance tends to be better if you can get more and more chips into a single silicon die. So more and more channels, I should say, into a single silicon die.
Okay, great. Thank you, Brian. And I'd like to thank Brian for an excellent presentation. And I thank the audience for the great questions and for attending this presentation. I also want to thank, really all of the speakers for their time and their participation. The CICC committee very much appreciates it. And we thank the audience, of course, too. So just a few reminders. This session, so this educational session, as I suppose all of them, they're recorded and they'll be made available on demand for playback. And we look forward to all of the audience members to attending the conference, which will be taking place over the next several days. I know it's a virtual conference and sort of challenging times, but I think this format that the committee found is actually quite good for a virtual conference. So it's a very good platform, and I hope you'll attend as many sessions as possible over the next few days. So with that, I will conclude this educational session. And again, one last time, I'll thank all of the speakers.